So in this subsection we covered the first order system. Higher order systems will be covered in courses that are more control oriented, either by my colleague David Rocher or by myself. The first order system is, you notice first order and first order over here. So a first order system is described by a first order differential equation. Okay, so this is where the name first order system comes from. And obviously a second order system will be described by a second order differential equation, and the behavior will be very different from the behavior of a first order system. Okay, so this is the first order differential equation, and we know that this is the time constant and this is the gain of the system. We had obtained impulse responses, step responses, okay, and what we'll do here is do the same and do it in the Laplace domain, and you'll see that it's often easier. Okay, well, to go to the Laplace domain we have to take the Laplace transform of this equation of here, and this is the resulting equation. Okay, say this is the Laplace transform of the derivative of y. Okay, so if we rewrite everything, we obtain this equation, and again in this equation we have two terms: the zero state response, the influence comes from the input, there is no influence from the initial conditions, so this is la réponse forcée in French, and we have the zero input response. That's the response that comes solely from the influence of the initial conditions. Okay, so in this case this would be our polynomial a of s, and this would be our polynomial b of s. Okay, you have got the a of s over here, and this one was called I of s. It takes into account the initial conditions. Okay, so we are now ready to obtain the transfer function of a first order system. Remember that the transfer function links the input to the output when the initial conditions are 0. So we should consider this equation with this term crossed out, and we see that the link between the input and the output is given by this rational function, which is the transfer function of a first order system, and this is indeed what is written over here. So this is here the transfer function of a first order system, and we know also that it is the Laplace transform of the impulse response of the system. So there are two ways now to obtain the impulse response. First way is to say, well, we know that the transfer function is the Laplace transform of the impulse response, and then we take the inverse Laplace transform of this one. Or we say, okay, we compute the response in the Laplace domain, we have to multiply the transfer function by the Laplace transform of the input, and since we know that the input is an impulse, a Dirac impulse, we know that its Laplace transform is 1. This is x of s over here. So the impulse response will be h of s. Okay, and to compute y of t, again, we have to do the inverse Laplace transform. Okay, so h of s, will write it a little bit differently. So here it is. So you can rewrite it as k over t 1 over s plus 1 over t. Okay, and if you do the inverse Laplace transform, you can see that, well, the impulse response is given over here. Okay, so this should look familiar. Let's draw it. So it will look like this, right? And at t equals 0 you have here k over t, and here the tangent here will bring you at t equals t. So you can also obtain the step response, and obviously here again it will be much easier to obtain the step response using the Laplace transform than to try solving the underlying differential equation. Anyway, you choose the method that you like, because this is something that you have to be able to produce at the time of the exam, okay? The step response of a first order system. So the response will be h of s times the Laplace transform of the input, and the Laplace transform of x of t, which is a unit step over here, will be 1 over s, okay? So y of s will be h of s times 1 over s. So we'll write it over here. So this is k s times ts plus 1. And we've seen that you can do a partial fraction expansion, and I'll leave you this as an exercise. But when you do it, this is what you obtain. Well, what we can maybe do is check. Remember that I'm a fan of checking things. So if we put this at the same denominator, you'll have ts plus 1. This one will give ts plus 1, okay, and this one will be minus ts, and of course the whole thing will be multiplied by k over here. So indeed you'll obtain this thing over here. So this is indeed correct. What you can now do is compute the inverse Laplace transform, and this will yield this expression over here. Again, we can have a look, but this should now look familiar by now. This will be the step response, and we'll assume that we at the input we have an input that is a step, so this is a 1 over here. And let us now look at the step response, and this will look something like this, right? This will be k over here. We know that in steady state the relation between output and input is the static gain of the system. And well, we can also have a look at the time constant. Well, the time constant, you obtain it by drawing the tangent, and you draw the other tangent when t is going to infinity, and when you go down over here you have t. So this is how this step response of a first order system looks like. So we can also have a look at the Bode diagram. Remember that what we do here is put a sign at the input, and we compute the steady state response, and we know that the steady state response will produce a sign at the same frequency, but that will be amplified by, well, a gain that is obtained by taking the transfer function, replacing s by j omega and taking the modulus, and the response is also phase shifted. And you do the same, you take h of s, replaced by s is j omega, and this complex number, well, you have to take its argument, and this will give you the phase shift. So let's do that. Here is the transfer function of the first order system. We evaluate it at s is equal to j omega, and this is the complex number that we obtain. And now we have to kind of compute the modulus and the argument. So what we do here is multiply by the complex conjugate of the denominator, and we do that at the numerator and denominator. So we end up with this expression here, and we do this because we want to decompose in a real part and an imaginary part of h of j omega. Okay, so this is the real part and the imaginary part you have over here, and you know that the modulus is the square of the real part plus the square of the imaginary part. You sum that and you take the square root, and the argument is the arctangent of the imaginary part over the real part. And if you do the computations, and I'll leave you these details, these are things that you have seen in previous courses, this is what you obtain, and you see indeed that, well, both the gain and the modulus of h of j omega and the phase shift, the argument of h of j omega, are functions of frequency. Okay, and as is said over here, well, we assume here that we have a stable system. That means that t is positive. If t is positive, you see that the pole is equal to -1/t, and it will be to the left of the imaginary axis, and the system will be stable. So we remember that we have found that the modulus of h of j omega is equal to k over the square root of 1 plus omega square t square, and that the argument of h of j omega is equal to minus the arctangent of omega times t. Okay, we can use these results to obtain the Bode diagram of the system, and the Bode diagram is actually two plots. The top plot is the, well, modulus as a function of frequency. Okay, so this is the frequency axis expressed in radians per second, and the bottom plot is the argument, the phase shift, as a function of frequency again. Okay, so we see that the frequency axis is expressed in logarithms of omega, so it's a logarithmic scale based on the log in base 10, as you can see. So this is omega is equal to 1, and this is omega is equal to 10, and this is what we call a decade, right? And in the top part of the Bode diagram, we see the modulus of h of j omega as a function of omega, and the y-axis is expressed in dBs. And so what we see here on the y-axis is 20 times the log in base 10 of the modulus of h of j omega, right? And this is dBs. So for instance, 0 dBs corresponds to a gain of 1. So here in low frequencies the gain is 1, and we see here that the bottom plot in the Bode diagram is the argument, the phase shift, and it's expressed in degrees. It could also be expressed in radians. Okay, and the reason why we use here a logarithmic scale for the magnitude is because you know that the logarithm, well, it's true in any base of, well, for instance, let's call it b times c, is equal to the logarithm in that same base of b plus the logarithm in that base of c. Okay, so the idea is that when you have, for instance, to construct the Bode diagram of h1 of s times h2 of s, what you'll will be able to do is, well, construct the Bode diagram of h1 of s and of h2 of s, and then you'll simply be able to add them because of this relation over here. So if you now take this result and you put the modulus of h of j omega, the gain of the system, as a function, and you plot it as a function of omega, this is what you obtain. And if you do the same with the argument and the phase shift, and you take this expression and you plot it as a function of omega in this, well, logarithmic scale, this is what you obtain. Okay, so let us have a look. Well, typically what you see here is that at low frequencies, well, the input signal will be multiplied by k, right? K is equal to 1 here, so it gives an amplification of 0 dBs, and there is hardly any phase shift, so y will be lagging, okay, the input signal only by a few degrees. And when the frequency is increasing, you can see that the gain will go down. Now you see that the gain is decreasing dramatically when the frequency is increasing, and the phase shift will finally evolve to minus 90 degrees. So this means that there is a lag of a quarter of a period. Well, instead of computing the exact formulas for the gain that you have, so the modulus of h of j omega and the phase shift that you got, and so the argument of h of j omega, well, it's sometimes easier to just consider the transfer function at s is equal to j omega, write it like that. Okay, so here we rewrite it a little bit differently by considering the cutoff frequency, and the cutoff frequency is 1 over t. You encounter here this relation between time and frequency, which is 1 over x relation. So this is what you obtain, and what we'll do now is consider the case where omega is much smaller than the cutoff frequency, omega is much larger than the cutoff frequency, and omega is equal to the cutoff frequency, and then see what happens. Okay, so if omega is much smaller than the cutoff frequency, well, this term over here you can kind of forget it, right? So what is left is k, right? So at low frequencies, much lower than the cutoff frequency, we see that the modulus of h of j omega is approximately k. Okay, and its argument, since this is, well, h of j omega is approximately k in this case, well, the argument, the phase shift, will also be approximately 0. So if omega is much larger than the cutoff frequency, well, we have the other term that becomes negligible. So we can do something like this, right? So h of j omega looks a lot like k over j omega c, and this is equal to minus j k omega c over omega, and this is minus j k over omega t, right? So now you can have a look at the modulus of this, and this will be k over omega t, and the argument will be minus 90 degrees. Okay, and then you can also have a look at omega is equal to omega c, and then you'll see that h of j omega is, well, this one will be equal to 1, is equal to k 1 plus j, right? And this you can write as k e to the minus j p over 4. I'll leave you this one as an exercise, and I have to divide by the square root of 2 over here. So you can see that the modulus is k divided by the square root of 2, and here that the phase shift is minus 45 degrees. Okay, so let us see if what we have just discovered can help us and draw the Bode diagram in maybe an easier fashion. Remember that we have considered this cutoff frequency. Omega c is 1 over t. Okay, t is equal to 1 over here, so we have omega c is 1 radian per second. So we had seen that at low frequencies, omega much lower than omega c, we had h of j omega is equal to, well, more or less equal to k. So k is 1 here, so if we express that in dB, so indeed we have a low frequency gain of 0 dB, and we had seen also that the argument of h of j omega could be approximated by 0 degrees, and this is what we see here. We hardly have any phase shift at all. We had seen also that at high frequency, so much higher than the cutoff frequency, well, h of j omega in modulus was, well, k over omega t, and we had seen that the argument of h of j omega was approximately minus 90 degrees, and this is what you see. So you have a phase shift of 90 degrees between the input and output sinusoids. Okay, so here I should put approximately equal to. Okay, so we see here that the slope is minus 20 dBs per decade. Let's have a look if we can, well, kind of see this. So if we call this frequency, let's say, or this one over here, we'll call it omega 1, and we'll call this one 10 times omega 1, so we can see what happens and have a look at this, but when expressed in dB, so we'll have 20 times the log in base 10 of k over 10 omega 1 t. So this is that one. So this one we can rewrite because I've written it before. The log in base 10 of b c is the log in base 10 of b plus the log in base 10 of c, right? So this you can rewrite as 20 log in base 10 of 1 over 10. This is minus 20 dB plus 20 log 10 of k over omega 1 t, right? So this is the gain that you have over here, okay, and you advance by a decade, and what you see here is that the new gain has decreased by minus 20 dB. So indeed we have a slope of minus 20 dBs per decade. And we can also have a look at the case where we are at the cutoff frequency. At the cutoff frequency we had that h of j omega in modulus was, now it's really equal, k of the square root of 2, and the argument of h of j omega was minus 45 degrees. Okay, so this corresponds, this is minus 45 degrees. And if you look at 20 times the log in base 10 of 1 over the square root of 2, you will see that it's minus 3 dBs over here. So what happens is that when you look at the low frequency gain, which is K, well, you lose here 3 dBs at the cutoff frequency. Okay, so what you can do to draw the top part of the Bode diagram, and the one that is related to the modulus of h of j omega, you can draw the two asymptotes, the low frequency asymptote, this is this horizontal line, and then we draw the high frequency asymptote, and the one that corresponds to high frequencies. And how you do this? Well, at the cutoff frequency you draw a line with a slope of minus 20 dBs per decade, so you get a very good approximation of the actual modulus of h of j omega, which is given here in purple, and the maximum fold that you make is actually 3 dB exactly at the cutoff frequency. Okay, so here at low frequencies you have 0 degrees, at high frequencies you tend to minus 90 degrees. So one approximation that you can use, which is rather good, is, well, to use a linear interpolation between the two that starts at 1 decade before the cutoff and that ends at 1 decade after the cutoff frequency. Okay, so you start to decrease the phase 1 decade before the cutoff frequency, right? And you make sure that you reach minus 90 degrees 1 decade after the cutoff frequency. And this, well, approximation here in sine, well, is rather a good approximation of the actual phase plot in the bottom part of the Bode diagram, and that is in reality an arc tangent. So the interpretation of the Bode diagram will be explained again later with an animation, but it's maybe good already to give an explanation. So remember that we are considering the response to an input signal sine omega t u of t, okay, and the omega, well, it's the omega that you see over here, right? And in steady state your system is going to produce, and it's very important to remember that it's the steady state, a sine at the same frequency, but that is going to be amplified or attenuated. It depends on, well, this modulus over here. So this is the sine at the same frequency plus a phase shift okay. This one you can read it over here, and this one you can read it over here. Okay, so depending on the frequency you will have different gains and different phase shifts. Okay, and this first order system will have a what is called low pass behavior. This means that, well, low frequencies, and low is always with respect to the cutoff frequency, which is this frequency over here, will tend to go through the system, okay, without attenuation, okay, and without phase shift. And that is if you at least consider that the gain is 1 over here. So this is a low pass behavior, because you see that at high frequencies, well, the signals tend to be more and more attenuated. So for instance, let us take a signal at omega is equal to 0.1 radians per second. You see indeed that the output signal in steady state will be hardly attenuated, and it will be phase shifted by only, let's say around 5 degrees. So what we'll do here is consider a system that takes the input and sends it to a delayed version at the output. Okay, so this is my system here, H, and it's described by this equation over here, and what you can do is go to the Laplace domain, and this is what you obtain over here. Remember that if the Laplace transform of x of t is x of s, then the Laplace transform of the delayed version is this one over here. Okay, so this system has transfer function e to the minus theta s, right? And if we are interested in the Bode diagram of this system that just simply delays the input signal by theta, we have to consider the transfer function at s is equal to j omega, and in this case this is what we obtain. So what we would like now is the modulus and the argument in order to obtain the Bode diagram. And what I often see when I ask this at the exam is lots of calculations, but this is really not necessary because all these things are obvious from this thing over here. Okay, so this is a complex number that is in polar form, so its modulus is 1. Okay, so this is the modulus of the h of j omega, and its argument is omega theta with a minus sign. This is what you've got over here, and so this is the argument of h of j omega. So you have to note that the argument here is expressed in radians. So this is our system, this is h of s, and we have just shown that the modulus of h of j omega in our case is 1 at all frequencies. It's independent of the frequency, and the argument of h of j omega is equal to minus omega theta. Right, so we can now use this to obtain the Bode diagram of this dead time system, of this delay system. And if we take the logarithm in base 10 and multiply by 20, we'll have 0 dBs at all frequency. Okay, so this is kind of obvious. Our system just delays the input system, so there will not be any amplification or attenuation. Okay, the gain is simply 1. Of course, if we do time shifting, there will be a phase shift, and this is what we observe. We observe here that when omega tends to 0, this is when we are looking this way, well, the phase shift is going to tend to 0 degrees, and this is what we see here. And we see that at a particular frequency, omega, which is 1 over theta, and in this case it's at omega is equal to 1 radian per second, well, we have a phase shift of minus 1 radian. Okay, so this is minus 1 radian, and if you express that in degrees, that's around 57 degrees. Okay, here we have a linear relation, but since we have here a logarithmic scale for omega, this is the shape it takes. Okay, so this is the Bode diagram of a dead time or delay system. So here we look at the Bode diagram of a first order, but this time with delay. We'll call this one h1 of s. We've considered the Bode diagram of this transfer function. It's the first order transfer function, and we've just considered the Bode diagram of the delay system, and this is h2 of s, and the overall transfer function h of s is simply the product h1 of s times h2 of s. We know that to obtain the Bode diagram we can simply add the separate Bode diagrams of this first order system and this delay system. Okay, for the amplification, for the gain as a function of frequency, we see that there is no difference because this delay system, well, it does not change the gain. Okay, we have seen that the gain is 1 over all frequencies, so we'll add 0 dB, and this is why the top part of the Bode diagram of a first order system with delay is exactly the same as the top part of the Bode diagram for a first order system. Okay, so obviously this delay here will cause a phase shift. This is what we do when we delay a signal, right? And we remember that this delay system was not causing any phase shift when the frequencies were very small, and this is indeed what we saw. And at a frequency equal to 1 over theta, and here it's 1 radian per second, well, this system is introducing an additional phase shift of 1 radian. So this gives us, well, an additional phase shift of around 57 degrees. Okay, so if we combine the two, if we add the two phase curves, we obtain the overall Bode diagram of a first order system with delay. So let's come back to this first order system with delay, and it is described by this transfer function, and let's have a look at how it can be described in the time domain. And we remember that the transfer function is, well, the Laplace transform of the impulse response. So if we take the inverse Laplace transform, we'll obtain the impulse response. Okay, so we have this delay over here, so let us maybe do the Laplace inverse transform of k over ts plus 1, right? This one we can write as kt over 1 over s plus 1 over t, right? This is the same, so we know that this inverse Laplace transform is k over t e to the minus t over t u of t, right? But here we have a delay, so we know that using this time shifting property we'll have k over t e to the minus, and here we have to put t minus tau over t u of t minus tau. Okay, and this is going to shift everything to the right by tau. And let's now have a look at the response of this system. So this is t, and this will be h of t. We put an impulse at the input, and what we'll see here is something like this. Okay, let's already draw the tangent and have a look at some indicators over here. So this will be theta, right? This will be k over t. Okay, so the amplitude, and well, when this tangent meets the x-axis over here, that will happen in theta plus t. Okay, so this is the impulse response of this first order system with delay. So let us have a look at the response, the frequency response of a first order system. It has time constant t equals 1. There is no delay, so it's a straight first order system. So this means that if the time constant is 1, omega c is 1 radian per second. And what we'll do over here is look at the output when the input here is a sine of amplitude 1 and with frequency 2 radians per second, so it's sine of 2t u of t. The response is given in purple. Okay, so it's a causal system that responds to a causal input, and you see the response in purple, and this response in purple will be composed of, well, two parts: the transient response and the steady state response. The steady state response I've shown in green, and the transient response, that's the one that disappears because the system is stable. And you can see here that after roughly 5 times the time constant, well, the actual response and the steady state response, they kind of correspond. Okay, so what you can infer from a Bode diagram is about the steady state response of the system. That means when the transients have disappeared. Okay, so what can you see in this Bode diagram? So 2 radians per second, that's over here, right? Well, you can see that there's an attenuation, and this attenuation is around -7 dBs. This means that, well, the amplitude of my output is now roughly 0.45, whereas the input was 1, and this is indeed what you see. And this you can obtain from the top part of the Bode diagram. Okay, and you can also see that there is a phase shift. The phase shift is what you see over here. It's this quantity over here, and it's -63 degrees. Okay, so the output is lagging by 63 degrees, and you know that in one period there is 360 degrees. So this lag that you see over here, it corresponds, well, to roughly a sixth of a period. Okay, this is what it means. One period is 360 degrees. Here we see roughly, let us say, 60 degrees, so it's 1/6 of a period. So here we have the same system. Okay, it has cutoff frequency omega c is equal to 1, and what we'll do is subject it to inputs that are sines of amplitude 1 with increasing frequency. You'll be able to see the frequency change when you look at the cursor, but the frequency will also be indicated on the slide, okay, over here, and you will be able to see the gain, well, here in absolute value, and here expressed in dB, and here you'll have the phase shift, but you'll of course be able to consider the effect. Okay, so in blue you'll have the input signal. It will always have amplitude 1. Of course the frequency will change, and the resulting, that's very important, steady state response of the signal will be shown here. So I should write it steady state here, is shown here in green. Okay, and obviously what you will see is that at low frequencies, lower than this one over here, the phase shift will be small and the gain will be approximately 1. When we approach here higher frequencies, well, the phase shift will be close to minus 90 degrees, and there will be of course a lot of attenuation. I will do a frequency sweep between 0.1 and 10 radians per second, and what I'll do is stop the animation at some spots. So let's have a look. So here I'm lucky, I've just stopped it at the cutoff frequency, and you can see here that you have indeed a gain that is minus 3 dBs. Okay, so roughly you have divided the gain by square root of 2, and the phase shift as announced is around minus 45. Okay, we can continue. So here I'm back again at a very low frequency, and here the gain is approximately 1 or 0 in dB, and there is hardly any phase shift. And here you see that there is a phase shift of minus 83 degrees. Okay, minus 90 degrees is a quarter of a period, right? So here it's a little bit less than that, and well, the gain is around 0.11. So we've seen before that a first order system has a low pass behavior. It is quite easy to construct a system that has a high pass behavior by simply constructing it from the relation 1 minus a low pass filter. And if you do this, you obtain this transfer function, and this has high pass behavior. Okay, let's have a look, and let's have a look at this high pass transfer function with s is equal to j omega, and this will be t j omega over t j omega plus 1, and you'll have to take the modulus of that, and this will be what you see in the top part of the Bode diagram. So if we look at omega that is much higher than the cutoff frequency 1 over t, what we'll have here is something that is 1. So indeed now we have a high pass behavior above the cutoff frequency. Well, the gain will not be affected as long as you're sufficiently higher than the cutoff frequency. So although this is not covered at the time of the exam, you see that there is the for your information logo. I want to say a little word about filtering. A filter is a system that removes undesired components from a signal. Most often the filtering will remove some frequencies or frequency bands. So we've seen the first order low pass filter, and in the previous slide we've seen the first order high pass filter, but it's also possible to obtain band pass filters and band stop filters. Okay, so important concepts are the cutoff frequency of a filter. Okay, it's the frequency beyond which the filter will not pass the signal. Okay, and usually it's at a frequency where the attenuation is 3 dB. Remember, for the first order system, which is a low pass filter, at the cutoff frequency we had indeed an attenuation of 3 dB. The roll-off is the slope in the Bode diagram, okay, beyond the cutoff frequency, and for a first order filter we had minus 20 dB per decade. Okay, sometimes you want a higher slope, and for that you have to use other types of filters, such as the Butterworth filter or the Chebyshev filter. They allow you to have a higher roll-off. If the filter has order n, then the roll-off will be minus 20 n dB per decade. It's possible to do quite a lot with Matlab and also with Octave. Some of you will actually have sessions, separate sessions with Matlab. So please do attend those sessions and be active and participate, because they allow you to illustrate the concept of the courses. And those of you who do not have to follow these sessions, well, maybe you can experiment yourself with Matlab and or Octave. So here's an example of a simulation with a first order system. So it's a first order system, okay, with gain 1, time constant 5, and well, a delay of 0.5. And so this is how the system is introduced into Matlab. And what you can then do is simulate the system for 25 seconds and obtain a step response, an impulse response, and also obtain the Bode diagram of the system. And this is what is generated: impulse response, step response. Here is the Bode diagram. Okay, so you can also compute the output of the system when it's subjected to an input sign using the command lsim. Okay, it's a sine at a frequency of 1 radian per second. So you can see here in the Bode diagram that will have an attenuation of around 10 dBs, right, and a phase shift of around 110 degrees. So if we look at the simulation, this is what you obtain: the input signal and the output signal. You say the phase shift appearing and also the attenuation, and you see here the effect of the transient that is disappeared, and here after 5 times the time constant, 25 seconds, the effect of the transient has disappeared. Okay, so you see that it's kind of useful to experiment with Matlab. So over here you have the Bode diagram of a first order low pass filter, and we use the butterworth command to have a third order low pass filter at the same cutoff frequency, and it's here 0.1 radians per second. So if we look at that, this is what you obtain, and you see that indeed the slope of this butterworth filter is now minus 60 dB per decade, because it's a third order filter. So you see here that you have something that is much steeper, and it's going to, well, separate what you filter out much better. Of course, since you have a third order filter, the phase will go to minus 270, and you could do something similar with a high pass filter. Again, a first order system and a butterworth filter. So what we do over here is generate some data. So there is a low frequency content, that's the sinusoid, and on top of that we have some noise, and so this is the signal that is generated. This in blue, the low frequency sinusoid, and the signal that is corrupted by noise. And so the idea is that when you're given the green signal, of course you would like to reconstruct the blue signal. So what you can do is use first order filters, a low pass first order filter and a high pass first order filter. These are the filters that we've introduced before, right? And then you can filter your corrupted signal, and this one will keep the low frequency content, and this one will keep the high frequency content. Okay, so in here you should have something that resembles the blue signal, and here you should have the high frequency noise. Using this first order frequency filter, this is the filter signal, and you see that it doesn't do too bad of a job. And this is the high frequency component, and you see here that it's doing a good job, but there is still here some low frequency influence because you're using a first order filter, and the roll off of the the filter is not high enough. If we are using a low pass and high pass but butterworth filter with here an order 3, and we use it to filter the signal, the corrupted signal, here we are going to retain the low pass signal and the low passed signal, and here we're going to retain the high frequency content. This is what you obtain, and here you see that you obtain really the high frequency content, and there is no low frequency component in this signal. So this is what you can do with a filter, right? Remove the components that are not of interest, and here it's high frequency components. So it is even possible to do a partial fraction expansion of this rational transfer function. You have to introduce the rational function as a numerator and denominator in Matlab, and then use the residue function, and as you will see, you will obtain the residues. These are the coefficients that you're looking for in the partial fraction extension, and what you have got here is or are the poles. And you can even use the symbolic toolbox to compute Laplace transforms. Okay, so you can even compute the Laplace transform of this signal and compute inverse Laplace transforms. Well, Matlab is only one of the possible programs that you can use in order to do signal processing. More and more people, even in industry, start to use Python. And if you want to use Python in a user-friendly environment, you can install the Anaconda environment. I've shown you here the web page anaconda.com, and if you go to products individuals, you can download the program and start working. Once you have installed the program, you will be able to open the Anaconda navigator, and you'll have lots of programs over here that allows you to do Python, to do computation, to do data visualization, and so on. And a nice environment is to work with the JupyterLab environment. So let's click. So what will happen here is that you go to a web environment in which you can work with Python, right? And it's an interface that looks a lot like the Matlab script environment. So without going into the details, maybe a few examples. Well, like in Matlab, you can define the symbolic variable s or the symbolic variable t, and then you can define a first order system just by encoding things like this, and it is recognized as a first order system. And then you can, for instance, compute the inverse Laplace transform. Okay, so this is the impulse response, and then, for instance, replace tau by 1. This is what you obtain, and for instance show the impulse response. You can do this, for instance, for several values of tau with different colors. And there is an example here. You have here the impulse response for a tau of 1, 5 and 10 respectively in red, blue and cyan. You can do something similar with the step responses. You can do convolution. Here is this first order lead lag system that we had considered in the course when we were looking at the initial and final value theorems. Okay, remember these step responses, and you can continue with, for instance, step responses of second order lead lag systems, second order systems with complex poles and so on. You can also, for instance, work with this SymPy environment and compute inverse Laplace transforms, and here are the two examples of Laplace transforms that have been tackled in the course, and you can see that this can be done symbolically using Python. I will come back to Python and JupyterLab at the end of the course, when we'll talk about, well, spectra calculation.